let's try a buffer problem. Okay, so essentially what we have is a weak acid. This is acetic acid, CH3COOH. We know its Ka value, we know its concentration. And we're going to be adding potassium acetate, which is the conjugate base of this. Okay, it's a salt as a base, basically. The K does nothing. CH3COO minus is the conjugate base of this. So we have an acid and its conjugate base mixed together, which is what makes a buffer. And we're hoping for a pH of 4.60. And we know we have a concentration of the acetic acid of 0.35. We want to know how much of the conjugate base do we need to add to get a pH of 4.60. Okay, well, the Henderson-Hasselbach equation, this is a weak acid, so this is the correct equation to use, is plus the log of concentration of conjugate base divided by the concentration of weak acid. Okay, we know the pH we're shooting for is 4.6. pKa we haven't solved for yet, but we can. So if you take, to get pKa, you're going to take the negative log of 1.8 times 10 to the negative fifth, because that is the Ka value. And if you plug it in, it comes out to 4.74. Okay, so in terms of these numbers here, we actually know most of this. This is just kind of some algebra here. So pH is 4.60, pKa is 4.74, which is encouraging. These numbers are near each other. If this was more than, basically this conjugate acid base pair has a pKa of 4.74, which means it's good for making a buffer anywhere between about 3.7 and 5.7, plus or minus 1 pH units. This is within that range, so it's acceptable. Plus the log of conjugate base and weak acid. Half the battle is figuring out which one's which. Honestly, what I'm going to tell you to do is there's two options. Whichever one has more H's is the acid. Okay, so we know our concentration of weak acid is 0.35, and we don't know our concentration of conjugate base because that's what we're solving for. I'm just going to leave it as an X. So literally it's just a bunch of algebra. Solve for X. Okay. We can't get rid of that logarithm yet, but we can subtract this off. 4.74. This will disappear, and this comes out to negative 0.14. It's fine that it's negative, we'll figure it out. And that is equal to the log of X over 0.350. So we need to get rid of this logarithm, so we're going to do 10 to the whatever on both sides. That goes away. And this side is 10 to the negative 0.14. And then we're going to multiply this 0.35 to the other side. So X is equal to 0.350 times 10 to the negative 0.14. Okay, plug that in the calculator. 0.35 times 10 raised to minus negative 0.14. Okay. It equals, and I get 0.254. And that's literally the entire problem. So the idea is, the reason this number is important is that basically, if we had a solution that was 0.350 molar acetic acid and 0.254 molar conjugate base, the acetate, we would have a pH of 4.6. So this should hopefully make sense. The pKa is 4.74. So if these things were equal, it basically cancel out, and pH would equal pKa. Basically, this divided by this, if they're the same, is 1. The log of 1 is 0. So these things become equal. So, but because we're shooting for a pH that is lower than 4.74, that means we're going to need slightly more acid than base. So these numbers seem reasonable, give us a pH of 4.6, which is what we're shooting for. So this should be the answer.